Our final lesson in topic 7 is 7.5, proportions in triangles. We're going to take a look at 3 theorems down below that help us create similar triangles. The first one is called the side splitter theorem. Inside of a triangle, if you have another segment that's parallel to that bottom edge, MN parallel to AC, notice how it breaks up that small triangle on the inside to the big triangle on the outside. It says AM over MB is equal to CN over NB. So take a look, that's that little segment to the big segment over here, little segment, big segment over here. That's called the side splitter theorem. One thing to note about this theorem down below, even though MN is parallel to AC at the bottom, it doesn't guarantee that AM is equal to MB. We don't know that for sure until we go to the second theorem over on the right. Our second theorem is called the triangle mid-segment theorem, and this is very similar to what we talked about with the trapezoid mid-segment theorem. For the if part, it says if DG is congruent to GE. So notice we've got the two segments the same on that side. That means G is the midpoint. And then over on the right, if FH is congruent to HE, so we have that double dash on the right, that means H is the midpoint on the right-hand side, and we connect that segment, that's called the mid-segment. Please write that down, the mid-segment. If we know that's true, then a couple of things down below are our conclusion. GH is parallel to DF, so we can add that arrow in. And now notice the formula. This is slightly different from what it looked like in trapezoids. Now GH is exactly half of DF, which should make sense because the segment on the inside should be smaller than the segment on the outside. And that's the triangle mid-segment theorem. Our final theorem on the right now talks about angles. This is called the triangle angle bisector theorem. So it says if angle UVX, so notice we use 3 letters here, from U up to V down to X. That's that angle on that bottom left-hand side. If it's congruent to VWX, the angle on the right, so WVX, sorry, I knew I said that in the wrong order, WVX. So if the angle on the left is congruent to the angle on the right, that means VX, that ray is the angle bisector. And what that does to your picture is a little particular. So this one's probably the trickiest of the 3. So if we know we have the angle bisector, then it says UX over WX. So take a look at that setup. UX is down here, WX is over here. That fraction is congruent to UV over WV. So notice we've got the 2 kind of segments on that one side and the 2 segments on the other side. So we'll be able to set up a proportion using that triangle angle bisector theorem. For the examples down below, if you didn't grab a calculator, be sure to do so now. You're going to want to try these cross multiplies to make sure that you can do this independently. In example 1, triangle JLN, it says if LN is 9.6, so from L to N, if that's 9.6, what are LM and MN? And then are the sides divided into proportional segments? Well, if we know that KM is parallel to JN, and we can see that with those arrows right here and right here, by the side splitter theorem, and we'll just go side splitter. We know that we can do JK over KL, and that proportion is going to equal NM over ML. So if we have 5 for JK and 3 for KL, well, now this is going to be a little tricky. Look at that right-hand side. We know LN is 9.6, but we don't know what the other parts are. So let's try to split it up. I'm going to say let LM equal X. So then to figure out how big NM is, That would just be the leftover from 9.6. We're not actually going to use just 9.6 in our proportion, but I can split mn up into 9.6 minus x. So whatever's left over from LM is what mn would equal. Oh, all right, so in our proportion then, to keep it consistent with the side splitter theorem, nm is 9.6 minus x. And LM is just whatever x is. We have a proportion, and now we can cross multiply. Ooh, and we might run out of space. So make sure you have enough room to write this. If I take 5 times x, that's simple enough. That just gives us 5x. It's the second one that's also a little tricky. If we take 3 times 9.6 minus x, watch what happens here. I'm going to have the 3, but then I want to make sure that the 9.6 minus x goes in a parenthesis. Be sure to add that in. From there, we have 5x on the left, but on the right, I've got to multiply 3 times 9.6, and that should give you 28.8. And then minus, I have to multiply the 3 by the x as well, and that gives us 3x. So now we have to make sure to distribute that 3 in to get rid of the parenthesis. Okay, so now we're just going to combine like terms. Notice I've got x's on each side of this equation. I'm going to move the 3x over, but we're going to add to do so. 5x plus 3x, I'm just going to bring this up over here, gives us 8x. And then on the right, the 3x's cancel, and we have 28.8. To get x by itself, I'm going to divide. All right, plug that into your calculator. 28.8 divided by 8. You should get a value for x of 3.6. Now remember, that was just part of that segment. We need to know 2 answers. So if LM is 3.6, that's 1 answer. I know, I'm sorry. I really wish we had more space here. To get that other answer, I'm just going to move this over a little bit so I have more room. To get MN, we have to do 9.6 minus 3.6. And that's not too bad. That just equals 6. That's what MN would equal. Now the second answer says, are the second question, are the sides divided into proportional segments? Well, we've already answered that. They are because of the side splitter theorem. So we would say yes. And we've already done the rest of the work. The next one, suppose BD bisects AC and CE. So notice point B on the left bisects the top and the bottom, and point D on the right also bisects that right-hand side on top and bottom. Would AE be parallel to BD? Well, yes, they actually would. And explain how you know. That's because of the triangle. And I'm just going to draw a triangle. Triangle, mid-segment, theorem. So we could put an arrow on the BD and an arrow on the AE to prove or show that they're parallel on that picture. And that's it for that problem. For this next example, I'm going to have you cross off a couple of things on the picture. As is, it looks pretty overwhelming, so I don't want to have us get too crazy with this problem. From U to V in the middle, I'm just going to have you kind of carefully just cross off the Y and that segment. We're just going to kind of get rid of that whole part. And then we're going to get rid of Z, but I want to leave that segment there. There, that's all I wanted us to do. Just cross off the segment from U to V, just kind of scribble it out, and then cross off that Z. Now it says, what is the value of X in triangle PQR? Well, take a look at where X is located. I see X on the left side and on the right side. But notice ST is parallel to PR. We've got the little arrow right here and the arrow right here. And what that allows us to do is figure out the little part to the big part on each side. So because of the side splitter theorem, we can say PS, this little guy right here, over SQ, PS over SQ, and that's that big segment right here on one side, equals TR, the little segment on the inside, over TQ, the big segment on the right. All right, so PS is x plus 2. SQ, well, if we take a look at the picture, it's a combination of 4 and 12. So together, the length from S to Q is 16. All right, on the right-hand side, TR is x. And TQ, that's going to be 9 plus 3, that's 12. Now we end up with a similar situation to that problem up above. So watch how we set this up. If I cross multiply 16 times x, that's 16x. Not so bad. But when we cross multiply the other way, I'm going to put the 12 out in front and then once again put a parenthesis around the x plus 2. We're going to end up multiplying the 12 to the x and the 12 to the 2. But I'm going to do that up here. My left-hand side stays 16x. And then on the right, if I take 12 times x, that just stays 12x. But then when I write the plus, if we take 12 times 2, 12 times 2 is 24. And now we're set up just like we were before. Let's get the x's on the same side. I'm going to move 12x by subtracting it. That moves it over to the opposite side. 16x minus 12x would give us 4x left over. And on the right, the 12x's cancel and we get 24. Last but not least, divide by 4 to isolate x. And x will equal 6. And for this problem, that's all we had to do. Flipping it over to the back page, we're going to cross off the try it. This question is related to the problem on the last page, so we're just going to start fresh with example 3. A reflecting pool is separated by walkways parallel to Lincoln Street and Jefferson Street, which are also parallel to each other. The city wants to add additional tiling around the pool. How much tiling does x feet represent? All right, so looking at this picture, let's kind of zoom in. We first want to figure out the length for x on the top left-hand side. So that's the segment right here. If we know that the walkways in between are parallel to each of the streets, they're going to be parallel to each other. So what we can do is apply the side splitter theorem. Now technically this isn't a triangle, but we are comparing those parallel sides. So if we were to extend this up in both directions, we would form that triangle shape. So we can still apply the side splitter theorem in this shape that kind of looks like a trapezoid, to be honest. All right, so if we think about how we could set this up, I'm going to zoom back out so I get a little bit more room on my paper. There we go. We could do x feet over 60 feet. Compare this side length to this one. And then on the other side, we could do 24 over 72. So kind of just the parts on each side. And look at that. We have one variable only. When we cross multiply here, we get x times 72, which is 72x. Easy enough. And then equals on the other side. 60 times 24, that's going to be 1,440. Double check that on your calculator, 60 times 24. Well then, to get x by itself, we'll divide by 72. Oops, get my 7 out in front there. There we go. 1,440 divided by 72 is going to be exactly 20. So it says how much tiling does x feet represent? It represents 20 feet. Well, then we have to go one step further. How much tiling does y feet represent? Well, if we take a look at our picture, y is in a different location, but we get the same type of setup. So now y is down here on that bottom right-hand side. So we can do kind of that same idea. If we set y over 72, that will be the same as 24 over 60. So y over 72 equals 24 over 60. And when we cross multiply, y times 60 is 60y. 72 times 24 is 1,740. and 28. Now to get y by itself, divide each side by 60, and we end up with y equals 28.8 feet. That's how much tiling they would need on the bottom right of that pool. And that's where we're going to stop for the video lesson. Please make sure you have everything written down in your notes.